Well, here we are. It's the psci 168 video lecture. psci 168 video lecture 4. And we have some great material today. I said we were going to learn about the shape and size of Earth. Simply, how is that even discovered? It's going to make some use of the mathematics we've already developed. And at the end of that, we'll kind of wrap up the whole section, what we're calling astronomy, you know, arithmetic, geometry, astronomy now. And I was going to start the force chapter, but I think we'll save that for next time because this will really wrap up this section. So our task was to discover the shape and the size of Earth. Not from a spaceship or anything like that, but from going outside and making observations. So shape and size of Earth, this is what we ended up with. And shape, question mark, and to know that, you have to know Earth is a heavenly body. And how do you know that? How do you know that the moon is not just a big lantern in the sky? So all of these things are discovered incrementally, but the picture that comes together looks like this. And this includes the sphericity of the Earth. But so yeah, I'm going to assume the sphericity of the Earth right now to discuss the Earth being a heavenly body because the geometry comes into play here. So let's go ahead and we'll have a pretty large size picture here. So imagine this is the Earth and you are standing right there, okay? And the sunlight is coming in from here. The sun is at some great distance. Sunlight is coming in right here. And for one thing, you can say this side of the Earth will be dark. Okay? And this side facing the sun will be light. Okay? Now, what if the Earth is rotating counterclockwise? If the Earth is rotating counterclockwise and I'm standing here, then is it sunrise or sunset? Well, we're about to be carried into the dark. Okay, so this is sunset, and if you see a moon at sunset, say the moon is over here, okay, then there's a dark side and a light side of the moon as well. And what do we see? We view this as a full moon because we're seeing the entire disk of the moon. So at sunset, if a moon is just coming up, as we'd say, it's a full moon. Okay. What if at sunset the moon is directly overhead? Okay. That's when we look up at the moon and we just see a half moon. We see a half moon that's directly overhead. We see a full moon here. And so we recognize that the moon is a heavenly body with certain geometrical properties. When we see the half moon, we're aware that it's, you know, half of a sphere. And if we were to see the moon over here at sunset, then you say, well, we're actually facing the dark side of the moon. But here I'll use red. We're maybe going to see a little sliver here. And so that's what we'll see if it's sunset and the moon is occupying that area of the sky. We're just going to see a little sliver. Okay. So this whole board that I've drawn up here, we could call the phases of the moon. Now, how about when the moon is right here, then the moon is actually in the Earth's shadow, and we see the Earth casts a shadow on the moon. That's called an eclipse of the moon. Eclipse of the moon. And if the moon is here, it casts a shadow on the Earth, and it's called an eclipse of the sun because it blocks out the sun. So we have phases of the moon, we have an eclipse of the moon, we have an eclipse of the sun. This board is showing the basic geometry of it, and from these types of observations, we infer that the sun, the Earth, and the moon are heavenly bodies. They cast shadows and other things like that. They are geometrical objects occupying space in different geometrical relations. So this goes way back, but until you hear it and think about it, you don't know it, okay? So the fact that the Earth is a heavenly body is dealt with, we could say, like, is dealt with these types of observations. So phases of the moon, eclipses of the moon, eclipse of the sun. You know, the moon casts a shadow on Earth. It blocks out the sun. So that's how we know the Earth is a heavenly body. And then we can ask about the shape and the size. So the sphericity, there's a number of arguments. One could just generalize and say, well, if the sun and moon are clearly spheres, then the Earth must also be a sphere. One could, so let me put this here in the notes for the shape. Earth casts an arc-shaped shadow. This is an observation that was made a long time ago. An arc-shaped shadow. If the Earth were, say, if the Earth were shaped like a book, then when it cast a shadow on the moon, the shadow on the moon would have a corner. Okay, but the shadow that's cast on the moon as the moon passes through the Earth's shadow is always arc-shaped. So that's one of the arguments for it, for the sphericity. Also, if you're standing on a high mountain near the coastline somewhere and you look over the ocean with a straight edge, you can actually directly see some of the curvature under the straight edge, right? The middle of the straight edge would be looking at the horizon. On the horizon, and you'd see the ocean curve under it slightly. So by the way, anyone ever has a chance to do this, take a straight edge along and report back to me. Okay, so anyway, for these reasons, it is decided that the Earth is a sphere. So we'll go ahead with the sphericity of Earth. Sphere. Okay. So now we want to know about the size of the Earth. So for the size of the Earth, there's a name that you could look up. In fact, everything what I developed right here, we're going to want to look up and get some nice printouts from the internet. So Eratosthenes look him up. Eratosthenes, some couple hundred years BC, Alexandria. So Alexandria was on the Nile River on the Mediterranean coast. Okay, so you have to look up. Alexandria is on the northern coast of Africa, the Mediterranean coast, on the Nile, and he was a scholar there. And then there's another city, Aswan, is about 800 kilometers south of Alexandria. That's on the Nile as well. There's a big dam there. You want to look that up as well. I'll come back to these things what we want to look up, because I'm going to just develop the argument. So what he reads is that on June 20, there's a well at Aswan that is illuminated. The bottom of the well is illuminated by the sun directly overhead. So at June 20th, the sun at noon illuminates the bottom of a well. This is how I heard the story, at least. The bottom of a well. Okay. And the implication is that the sun is directly overhead. Now in Fresno, the sun is never directly overhead at noon. It's always coming in at some angle, okay? But at Aswan, it'll be directly overhead. That's because of the latitude of Aswan. Okay, so on June 20th, the noon sun illuminates the bottom of a well, means directly overhead. And here's the idea that Eratosthenes had. So this is these sketches, by the way, when you're making these sketches in your notes, the bigger the better, because we want to make them neat and label them so we can understand the geometry. So here's the spherical Earth for Eratosthenes. There's the radius of the Earth from here to here, and this happens to be Aswan. I'll even draw the idea that, you know, the sun is illuminating the bottom of a well. So the ray of the sun coming in, that means it's directly overhead. So up, if you're standing on Earth, is always away from the center. So if we were standing over here, for instance, then that's the up direction, right? And here the up direction is directly overhead. So Eratosthenes reads about this in a book, and he's in Alexandria. Alexandria, we're going to say, is right here. Okay. And straight up and down is this line I've extended. And the sun coming in at noon is coming in from here. So these are parallel rays. That's an approximation to reality. They're not strictly parallel, but for the geometry problem, he assumed parallel rays, sun, right? Parallel rays coming in. And he measures an angle here, 7.2 degrees. So this here is Aswan. This is Alexandria. Now, how does he measure that angle? There's a number of ways, but I just wanted to show what this angle means. So if straight up and down is my ruler, then that's the straight up and down. Okay, so if straight up and down is my ruler, then the angle to the sun is this one here. So at noon, for example, I'm standing here, there's straight up and down, and the angle towards the sun is what the angle my arm makes, okay, with the straight up and down ruler. So that's the 7.2 degrees that Eratosthenes measures. It takes a little while to relate this geometry to what you're actually experiencing outside, but we've already spent a little time talking about angles and shadows and sundials. Okay, so there's the idea. And this distance of the arc length, S, is equal to 800 kilometers. 800,000 meters. A kilometer is 1,000 meters. So 1 kilometer equals 1,000 meters. Okay. So yeah, that's a perfect geometry problem, and Eratosthenes knew geometry. So here's the thing, if these lines are parallel, we have an angle here, theta, that we can identify with that angle in the middle. And since we know the distance north-south from Alexandria to Aswan, and we've measured this angle, we can now determine what the radius is, just using the very basic geometry. So let's go ahead and do that here. It's actually a good homework problem to assign, but I'm gonna do it for you. But make sure you're able to do this calculation. This is often a test question I like to give. So you've seen it in the, you've seen it in the lecture, and I do a related test question. Of course, this semester all the tests are being taken at home, open book, so I'll have to cook up something somewhat related, but not exactly like this. But I actually do like on test questions to have students just write out this kind of scenario here in their own words. Okay, so back to the problem at hand. We want to find the radius. So find the radius of Earth, R, and the argument is this. We can say that arc length S is the same proportion of the entire circumference as that angle 7.2 is a fraction of 360 degrees. And in symbols, we have S divided by 2 pi radius, that's the circumference, right? It's like the circumference of a slice of a piece of pizza, okay, is equal to 7.2 degrees divided by 360 degrees. So right there is the answer. We just have to solve algebraically for R. Okay. Now, you want to get as much practice as you can in the semester doing these kinds of little algebra problems. And there are many ways to do them. First, we could just flip both sides. 2 pi r over s is equal to 360 degrees divided by 7.2 degrees. As many steps as you need to do something like this is fine. With practice, it just becomes easier. And what you'll notice is I always hold off on plugging numbers in as much as possible. So yeah, we flip this. We have 2 pi r over s, 360 over 7.2. Now we're just going to cross multiply. So here's what I'll do. I'll just show you, for those of you who haven't done this in a while. Now that I've done this, I can multiply both sides by s and divide both sides by 2 pi. And then s cancels, 2 pi cancels, and I'm left with r. So I'll write down for us r is equal to s 2 pi 360 divided by 7.2. S is equal to 800 kilometers. Now go ahead and leave room in your notes and actually take out your calculator and do this. You're going to get approximately R is equal to 6.37 times 10 to the 3 kilometers. And we'll go ahead and say radius of Earth is equal to 6.37 times 10 to the 6 meters. So we'll go ahead and express our astronomical quantities in scientific notation in meters. If it's off by a digit or two here in this thing, that's fine. Okay, this is rough numbers. This is the one we'll use. So what you see is you just have this chain of inferences. A measurement had to be made. A measurement had to be made. And you could say a couple measurements. You had to know the north-south distance. You had to make that measurement of that angle on June 20th. It has to be the same day that the sun shines straight down there. And then you have to have this idea. You do the calculation. Now you actually know how big the Earth is. And remember we had that Powers of 10 video I put in our playlist. I hope everybody watched it. Watch it more than once. In fact, if you watch it again, you'll recognize the rough size of Earth that was mentioned in the video. I also sent out the transcript, so it came out pretty clean. Go ahead and print that transcript out, put it in your book as well. So now I want to say a bit about what we want to add to our book in terms of this. This is the whole scenario, and you want to look a few things up. Let's check our time here. Okay, good. Yeah, so we have this. Make sure you do this calculation. Make sure I didn't make a mistake. And I'll get a little list. We'll call this homework. It's just what you want to put in your book. So if you haven't done it already, let's go ahead and start a list. Homework 1, print out Eames transcript. And by the way, that means all these things, you should lay them out somehow, take the pictures of them, send them in along with your notes, right? So I see that all these things have been done. So print out the Eames transcript. Eratosthenes, look him up, maybe there's a wiki page on him. What are his dates? When did he live? A couple hundred years BC. Then we want some maps. So if you can go on, say, Google Maps and get some good map images, take some screenshots and print them out. And then depending on your editing skills, you can put more than one thing on a page. It doesn't have to be a full page for everything. So you can organize this stuff to make it as beautiful as you want your book to be. So what we want is maps that show that show Egypt, the relation to the Mediterranean and Africa, so maybe a larger scale, then zoom in a bit. That show, I'll just write Egypt, Alexandria, Aswan, so that will illustrate where this thing was done and how it goes, and how these various lengths. Maybe you could even try to get that off of your map, that distance between those two cities. Note the latitude of Aswan. Note the latitude of Aswan. And that has to do with the tilt of Earth's axis. The tilt of Earth's axis with respect to the orbital plane. Because what does it mean for that well to be illuminated by the sun directly overhead? If the sun's coming in like this, right, then you have to be at that particular latitude, okay, say a certain latitude north of the equator, that will correspond to the tilt of Earth's axis, okay? So note the latitude of Aswan and the tilt of Earth's axis. And then I want you guys to get a little table of astronomical data. So what I've shown you now is how we can measure the size of the Earth in millions of meters. And if you look at if you looked at the Eames video, you saw there were all manner of lengths being discussed, and you can ask yourself, well, how do they know that? Well, now you know the answer to one of them. You know how we know that the Earth has a certain size. Now, it's possible for us to talk about the moon and the sun, their sizes and distances, but that takes more time than we want to spend on this. But we can be satisfied to have learned this one, and what I'll just ask you to do is print out a certain number of these data as well. I used to just write these on the board out of my notes, but if you look them up, it'll be that much better, okay? It'll be that much better. So continuing this list, now that we have one example of how these measurements are made, the role of geometry, the role of observation. So let's just call this table of astronomical magnitudes. That sounds pretty. Table of astronomical magnitudes. So what we now have is Earth and the radius. I'm going to name it capital R sub E, and we know that's 6.37 times 10 to the 6 meters. So let's see what else we can have here. Earth, we haven't gotten there yet, but now's the time to write them down. So Earth, the mass, M equals so and so many kilograms. You can find, I'm sure we can just type this in and find it. Then we're going to have for the moon, radius R sub moon is equal to so and so many meters. We're going to have Earth to the moon distance, and I'll use lowercase r for distances. Distance from the Earth to the moon, so and so many meters. And I'll put a note there. If you look up the exact number, it turns out that the exact number is a rough approximation of 60 times the radius of Earth. So if you want to visualize the Earth and the moon and their sizes, this is an important thing. Earth-Moon distance, and let's do two more here. The sun, our sun, radius of the sun is equal to so and so many meters, and then the Earth to the sun distance R sub Earth sun is equal to how many meters? I'll put question marks here. Yeah, so you can just look those up and make sure they're in meters and print them out. And I have one more thing here. Finally, don't miss this one. Mass of the sun. Mass of the sun, so what did we have here? Mass of Earth was m sub Earth, and mass of the sun, m sub sun, kilograms. We haven't introduced kilograms yet. We will systematically because we're going to talk physics pretty soon. This was all geometry and astronomy, but these are all very useful things. So if we had more time, we could give geometrical arguments for radius of the moon, these distances and sizes. The masses we would not be able to get by geometrical arguments. These two masses we would have to get by physics dynamical arguments. That'll go a little farther than what we'll do in this class. But you guys can go ahead and write them down, and you'll have a nice little chart there at the end of this section, which is what this is. In terms of images, so we're printing these kinds of things out. If you want to put in some interesting astronomical images as well to go along with your table, fine, you can do that too. Yeah, so we want some images. You can see the homework in terms of your book is taking shape now, and I'll come up with a grading scheme for the homeworks. Basically, the notes, you should be aiming for 100% credit, because I really just look at them and check off that you did them. But I can see the difference between doing a really good job and not, so I'll do a bit of a gradation on that as well. But I've seen some really good notes already from all of my classes, and that's a major part of this, because of the style of our semester now. If you can work your notes and construct something useful, true, beautiful, then you'll get something. It won't be a wasted, there's no wasted semester here, okay? We're really gonna learn a lot. Good, let's see how we're doing time-wise. Yeah, for today, I think this half hour is just the right thing, because I've left you with a number of things to do, and as you go ahead and write these notes out, try to understand every step. These are not things that we just understand automatically just by copying it, so you have to do a second run through your notes, a second run through the lecture to start to understand these things. That's really the nature of math and physics. You can't just learn it by writing it down and seeing it once and memorizing it. You actually have to do it. So I think you'll enjoy these things here, these little calculations that I did, the construction, think about it. Should I add that to the homework? No, I won't. But we could generalize this thing. So understanding this argument, then we can think of ourselves between, say, us and San Diego. Could we get on the phone with our colleagues in San Diego and do a measurement like this between two cities that do not have the sun directly overhead? That would be kind of fun. And the answer is it would be possible, but the precision would, of course, be difficult. Okay, I think we have enough to do here. Get these notes clear, get as much of this as you can, and take pictures. Remember the homework, you're always taking pictures and showing me that you did it. And finally, I'll just say the next lecture, so I'll leave this with the next time so that we see where we're going. Now that we've done geometry, astronomy, measurement, the meter, got that one here at all times. So next time, force. And force, a push or a pull, muscle sensation, your weight on the bathroom scale, that's a force. And we're going to get into forces also in terms of the geometry that we've learned, so it's an interesting section. It's on our way to talking about energy. We have to go from geometry, we needed force, we're going to do next. Okay, good. See you guys next time.